Chemistry is a science for the 21st century. Chemistry is involved in so many different things. This gives you some idea. Health and medicine, sanitation systems, surgery with anesthesia. Without anesthesia, there would be no surgery. Vaccines and antibiotics, gene therapy, all the stuff that we have today. Energy in the environment, different types of fuels, materials and technology, polymers, ceramics, all the stuff that you have at home, the clothes you wear, the computer that you're using, all this stuff is involved in materials, and chemistry is vital to the production of those. Now, in the study of chemistry, we go from the macroscopic, which means what we can see, and we try to interpret what's happening on the microscopic or the atomic level. So we have to make up models to picture what we think things are really like. Even though they might not be exactly like this, they just help us to get a better view of what's going on. Now, we use a scientific method in problem solving, and this is an example of that. First of all, we have to make observations. Observations can be qualitative or quantitative, meaning you could say something like a person was 6 feet tall. That would be quantitative. Or you can just say the person was tall. That would be qualitative. They can sometimes try to make you come up with a better observation. So you might say, can you qualify that observation? So you might say, well, somebody is taller than me, and that helps to narrow that down. So we have observations, and then we have what they call representation. This is where we try to figure out exactly what's going on there. We might make hypotheses, and then test our hypotheses, and then we try to interpret them. And the arrows show you that this process is ongoing, on and on and on. So a hypothesis, which really means little idea, is a tentative explanation for a set of observations. A tentative means it might not be a true explanation, but we always have to test it. So we test it, and we can modify that hypothesis, and we can change it all the time. So hypothesis is not the same as a theory. A law, on the other hand, is a concise statement of a relationship between phenomena that's always the same under the same conditions. Laws many times are mathematical. Now here's an example of one. Force equals mass times acceleration. Now this doesn't explain what's going on, but it's a statement which we could then say is an equation and use it to calculate the force that is necessary to, let's say, to accelerate a particle with a certain mass. In chemistry, you're going to learn a lot of gas laws. We have things like Boyle's law, Charles' law, law of Gay-Lussac, Avogadro's law, and all of those will have little formulas with them. A theory, on the other hand, is an explanation. So it explains everything that we have seen, and it also should be able to predict what we will see in the future. Now, theories also come and go, so a theory is really best written with pencil. Now, here's an example. Here we have the atomic theory. The atomic theory explains about rusting. And we have our oxygen molecules here, we have our iron atoms down here, and then we have what we feel is the formula for rust. It's Fe2O3. So that's our interpretation of it. But even the atomic theory has changed over time. It's had about 6 different things added to it and taken away from it. Now, chemistry in action. This is right out of the text. In chemistry in action here we see primordial helium and the Big Bang theory. So, 1940, George Gamow hypothesized that the universe began with a gigantic explosion or a Big Bang. Now, he hypothesized it, meaning he said that's how it began. But we have to have some evidence for it. So, what are these experimental evidence? The universe is expanding. And they can see that the universe is expanding because of the radiation that's being produced. The radiation that's being produced tells us that things are moving further away from each other. If you go backwards then, you can come up with a spot where everything was all together. And then right after that, it exploded. So, chemistry is a study of matter and the changes that it undergoes. There'll be a few definitions we want to make sure we get down. Matter, anything that occupies space and has mass. A substance is a form of matter that has a definite composition and distinct properties. Substances can be elements or compounds. And then we have some examples here. We have liquid nitrogen. You see how cold that is. That's, wow, about 200 degrees below zero. We have gold ingots. These are just little bars of gold. And we have crystals of silicon, which is similar to what's in your computer. A mixture, on the other hand, is a combination of two or more substances in which the substances retain distinct identities. And we have different types of mixtures. We can have a homogeneous mixture. Here's an example here. You have a soft drink like you have at home, milk, or solder. Now, solder is used in welding. The thing about homogeneous mixture is it doesn't look like a mixture. It looks like it's one material. The only way to tell it's a mixture is try to take it apart. The other type of mixture we have is called a heterogeneous mixture. And a heterogeneous mixture is one that's obviously a mixture, but we can see at least two different things in it. Now here will be an example. Cement and iron. Cement, iron filings and sand. When you look at cement, you can see the different particles in it. Another example could be, for instance, a blueberry muffin. You can see the blueberries and you can see the muffin part to it as well. Now, vanilla ice cream, on the other hand, would be homogeneous because it just looks like one thing. So now we're going to check out physical properties versus chemical properties. Physical means it can be used to separate a mixture into pure components. Here's one where we can separate mixtures. We can use a process called distillation. Now, in distillation, we have a distilling flask and we have a heating mantle. We don't want to use a flame because maybe something that we're making is flammable. And we're heating this mixture in the flask, and something will turn into a vapor. The vapors rise up here into this fractionating column. Now, in a fractionating column, what happens is the particles with the smallest composition will continue on up into the condenser, whereas the heavier ones will turn back into a liquid and fall back down into the distilling flask. And they usually have little things in here in that fractionating column for these gases to adhere to. Now, if the particles are small enough, they continue on into the condenser, and this condenser is covered by water. And the water will cool down the vapors and make them condense to a liquid. So here we have one of the components then that was in the original mixture. And here's an example of also separating a mixture using physical means. We could use a magnet to separate iron filings from sand. See how the iron filings are grabbed onto the magnet and leave the sand behind. An element is a substance that cannot be separated into simpler substances, that is, by chemical means. And we have 114 elements so far. 82 elements occur naturally on Earth. Here are some examples. And we can see them here. We have aluminum, and you've seen aluminum before. There's aluminum nails. You might not realize this was aluminum like in the fencing. We have some sulfur here. 32 elements have been created by scientists. Now this is since World War II, and these are all radioactive elements. And here's a list of the elements here. These are the common ones. Now you should know these elements and their symbols. Especially pay attention to the elements that come from the Latin names, like copper. The element symbol is Cu, or we have like iron is Fe, or lead is Pb. So these are easy to remember, but also easy to mix up sometimes. So you should know these. A compound, on the other hand, is a substance composed of atoms of two or more elements chemically combined in fixed proportions. Now, fixed means constant proportions. Now, let's take a look at some examples. Okay, so we have lithium fluoride as a compound. It's composed of one lithium and one fluoride. We have some quartz here, and we have some dry ice, which is carbon dioxide. Now, as far as the fixed goes, carbon dioxide has the formula CO2. It's never anything else. It's not CO3 or C2O7, anything else like that. And this is a little diagram that shows matter all being separated into its various components that we just went through. We can classify matter different ways. And one way to classify matter is by the state that it exists at room temperature. So at room temperature, we can have solids, which usually show a nice even arrangement like that. We can have liquids, which don't have that nice even arrangement, but they all kind of stay in the same place. And then we have gases, which have a lot of space between the particles, and they occupy whatever volume is available to them. We can see those three states of matter by just looking at water. So we have a block of ice down here, and here are the water molecules all bonded together. And these little dots represent hydrogen bonds, which hold the water molecules to each other. And then what happens to the ice melts and forms liquid water. We don't see many hydrogen bonds anymore. And then we have also steam being created here, or water vapor, and now you see there's a lot of space between the water molecules. But what kind of changes can matter undergo? Matter can undergo a physical change, which doesn't alter the composition at all. And here are some examples. You can have ice melting or sugar dissolving in water. Now when ice melts, it just goes from solid ice to liquid water, but the formula is exactly the same. It's still H2O. And for sugar dissolving in water, sometimes people think that's a chemical change because the sugar seems to disappear. But if you taste the water, you can taste the sugar, so you know it's still there. Now a chemical change, on the other hand, alters the composition of the substance. Many times a chemical change will also have a physical change going along with it. Now one difference here is that a physical change can be reversed by simply changing what you just did. For instance, if you melt ice by heating the ice and you get water, you can just cool the water and get the ice back. A chemical change, on the other hand, can be very difficult to reverse. So the common chemical changes that we see at home are really not reversible. And here's an example of a chemical change. We're taking some oxygen and hydrogen gases and burning them to make water. You can see a flame here. Now we can put properties, and these are really physical properties, into two categories. You can have what we call an extensive property, which is a property that does depend on how big the sample is that you're considering. An example would be mass. So for instance, you can have a certain mass of gold. You can have any old mass of gold, and just knowing the mass itself doesn't identify the substance as being gold. So that's going to be a property of just that particular sample. Length would be another one. Volume is another one. Volume here we have our graduated cylinder. Now an intensive property, on the other hand, does not depend on how much you have, and can be used to identify a substance. One example would be density, which I'm sure you're going to do in the lab. Another property is temperature. Now, although this doesn't identify what a substance is, you know that if you have 2 glasses of water, of different amounts of water at home, and you took them out of, let's say, the refrigerator at the same time, they're both going to be at the same temperature. It doesn't matter how much of the water you have. Color is another one. You know, gold has that nice bright yellow color. Doesn't matter how big or small the sample of gold is. So matter is anything that occupies space and has mass to it. Now, in the metric system, here we're going to be using the International System, abbreviated SI. The unit of mass is the kilogram. And the kilogram is about a little over 2 pounds. And you can see 1 kilogram is going to be equal to 1,000 grams. And this is it in scientific notation. Weight, on the other hand, is not quite the same as mass. Weight is the effect of gravity on an object. So you know that when, for instance, the astronauts go to the moon, they seem to weigh less on the moon, yet their material, their matter, hasn't changed at all. Just like when the astronauts go up into outer space at all, they have what they call weightlessness, but they don't have what they call masslessness. Here we have a couple of astronauts on the moon here. So the weight equals c times mass. So on Earth, c is equal to 1. In other words, there's no real effect here. Comparing that to moon, the moon, c is much less than 1, and c is the effect of gravity. So gravity, if we call gravity 1 on Earth, then weight and mass are the same. So on the moon, gravity is much less, so therefore you weigh much less. So here's an example. A kilogram bar will weigh 1 kilogram on Earth, but only weigh 1/10 of a kilogram on the moon, because gravity is only 1/10.